Today I'm talking about Kalman filter. Kalman filter is a highly efficient recursive filter which can estimate the state of a dynamic system from a series of incomplete and noise continuum measurements. Kalman filter will consider the joint probability distribution at each time based on the value of each measurement at different times, and then generate estimations of unknown variable. So it will be more accurate than the estimation based on a single measurement. First of all, we have an estimation for each state, such as the distribution on the left. This is our optimal estimation of the current state. Our estimation of the current state has actually many possibilities. All we have to do is use our current state to estimate what our next state will be. This is Kalman filter. Because our prediction is not accurate, we need to measure the state and optimize our estimate by measuring the state. This is an update operation in the Kalman filter. The variance of the observed probability distribution represents the noise, and the true value of the measurements at the same time is also in the distribution, but it cannot be determined. Now that we have predictions and measurements, we need to find the more accurate estimation for the next state. How to find it? First, the prediction of the next state is a Gaussian distribution, and the observation of the next state is also a Gaussian distribution. By combining these two Gaussian distributions, you can get a Gaussian distribution in the middle, which is the updated optimal estimation. The core idea of Kalman filter is actually these 5 formulas. Next, I will use an example to roughly introduce the principle of its algorithm. Suppose a car on the road with a position P and velocity v to indicate its current state. In addition, the driver can accelerate or decelerate. U is used here to indicate the control quantity of the car. Kalman filter assumes that both variables should be random and conform to a Gaussian distribution. In our exam, it's position and velocity. If we know that state xt minus 1 at the last moment, what will the state xt at the current time be? So we write this state equation. This is the first formula, the state prediction formula, where F is the state transition matrix, indicating how to infer the state at the next moment from the state at the previous moment. B is the control metric, indicating how the control quantity U acts on the current matrix, where X is an estimated value because the true state of the car we don't know. We can only estimate the value of X as much as possible based on observation. The superscript of X on the left indicates that this was predict value based on the state of the last moment. Later, we will have to correct this X based on observations. With the state prediction formula, we can predict on state at current moment. But we know that all prediction contain noise. The greater the noise, the greater the uncertainty. We use a covariance matrix P to indicate how much uncertainties this prediction brings, and to multiply it by the state transition matrix to let this uncertainty pass over time. That is, to infer the covariance of the current moment from the previous moment. This is a property of the covariance matrix. This is something we still have to consider. that is, our prediction model is not 100% accurate and contains noise itself. So we add Q to represent the noise brought by the prediction model itself. This is the second formula of the Kalman filter. It represents the relationship of the uncertainty at different times. Suppose we put a sensor at the end of the road. We can observe the position or velocity of the car at every moment, and the observed values is counted as zt. Then there is a relationship from the state xt to the observation's state zt, which we call observation matrix H. Because observations are not 100% reliable, so we add V to represent the observed noise. The covariance matrix of this noise is represented by R. So we have the obtained xt with a minus sign. Now we only have to add the correction value to get our best estimation. First, look at the part inside the bracket. That represents the residual between the actual observations and our expect observations. This residual is multiplied by a coefficient k, which can be used to correct the value of xt. It is called Kalman gain. It has two main aspects. The first is to weigh the covariance P of the prediction state and the covariance matrix R of the observations to determine whether we believe in more prediction models or more observation models. If you believe that there are more prediction models, the weight of the residual will be smaller. And the second function is to transform the expression of the residual error from the observations domain to the state domain. So, how can we use the residuals of the observations to update the state value? In fact, the Kalman coefficient k is doing such a conversion for us. The last step is to update the noise distribution of the best estimate. The value is reserved for the next iteration. In this step, the uncertainty of the state is reduced. In the next iteration, the uncertainty will increase due to the introductions of the transfer noise. The Kalman filter seeks a balance among changes in the uncertainty. Now, I will summarize the process of Kalman filter. Kalman filter is actually the process of fusion of two Gaussian distributions, one predicted value and one observed. First, based on the original optimal estimation, the state transmission matrix and the control matrix and the correction vector, the last optimal estimate is obtained, and then the new correction correlation is obtained through the correlation of the original two distributions. Then obtain the Kalman gain k from the observations to optimize our prediction. I have already introduced a Kalman filter for linear system. When the system is a linear Gaussian model, the filter can give the best estimation. But the actual system always have different degrees of nonlinearity. For nonlinear system, one method that can be used is to convert the nonlinear system into an approximate linear system through linearization, that is EKF. The core idea is expand the nonlinear function into a Taylor series around the filter value and omit the second order and higher order. An approximate linearized model is obtained. Then apply Kalman filter to calculate the state estimation. Shown in the figure, the right side is the algorithm structure and steps of the classical Kalman filter we're already familiar with. And the left side is of the extended Kalman filter, where we can see the red area are different. It can be seen that the algorithm structure of the two filters is almost same, and there are only slight differences in several equations. But in the left figure, we still see capital F and capital H. In a nonlinear system, the method of obtaining F and H involves the linearization mentioned earlier. So, calculate the partial derivative of x for f at estimate x in a nonlinear system, then we obtain f. Calculate the partial derivative of h at xg in the same way of h, we obtained capital H. That is, in the extended Kalman filter, the prediction of the state and the prediction of the observations are calculated by the nonlinear function, and the state transition matrix F and the observation matrix H are replaced by the Jacobian matrix of the F and H functions. The Kalman filter has many applications, including applications in control, navigating, computer visions, etc. For example, in image processing, Kalman filter is applied to restore blurred images caused by some noise. After making certain statistical properties of noise, Kalman's algorithm can be used to recursively obtain a real image with the smallest mean square error from the blurred image, so that the blurred image can be restored. Here, these examples illustrate how to use a Kalman filter for tracking objects and focus on three important features. First, predictions of objects' future locations. Second, reductions of the noise introduced by inaccurate detections. The third, facilitating the process of associations of multiple objects of their tracks. Before showing the use of Kalman filters, let us first examine the challenges of tracking an object in a video. The video shows a green ball moving from left to right on the floor. The white regions over the ball highlights the pixel detected using MATLAB, which separates moving objects from the background. The background subtractions only find a portion of the ball because of a lower contrast between the ball and the floor. In other words, the detection process is not ideal and introduces noise. To easily visualize the entire object trajectories, we overlay all video frames onto a single image. The plus marks indicates the centroids computed using a blob analysis. After using Kalman filter, we can see the result. There are two distinct scenarios that the Kalman filter suggests. When the ball is detected, the Kalman filter first predicts its state at the current video frame, and then uses the newly detected object locations to correct its state. This produced filtered locations. When the ball is missing, the Kalman filters solely relies on its previous state to predict the ball's current location. Yeah, that's all. Thanks.